In this exercise, we're going to use the MGF of the geometric distribution to give another proof of that the mean of this geometric distribution is q to the p, q divided by p, and the variance is q divided by p squared. So this problem requires that we calculate the MGF. The MGF of the geometric is given in chapter 6 in Blitzstein, but we're going to start by redoing it just to see exactly how it was derived. So let's set a random variable x as geometric with parameter p, and then the MGF of x is the exponential by definition to the tx. And so we now calculate this expectation and see what the MGF is more precisely. And then after that, by theorem 645, page 280, we're going to then take the first derivative and the second derivative to get the first and the second moment. I'm going to prove this theorem in another video, but this is the theorem that we're relying on when we're going to calculate the mean and the variance of the geometric or any random variable. Alright, so by definition, we use lotus and the PMF of the geometric. So the geometric starts with I up to infinity. Whoops. Lotus, by lotus we are just taking the transformation of x like this, and then we take the PMF of the geometric, which is 1 minus p I and p. Okay. Moving ahead here, we see you can take out p like so. And then we have, well, there's a little slight error here. The index is unclear, so I, just to make this clear, let's change I for little x here. That makes it clear. So these are the number of failures in the geometric distribution before we're getting one success. And so the index now runs over all the x's here. Okay? And realizing now that we have the power to the x, we can then write e to the t 1 minus p like so, and e to the t is just a constant for whatever t we choose. By the MGF, if the MGF exists, this interval t has to contain 0. Okay, so now we see that this expression here amounts to a geometric series of the form I from 0 to infinity, e to the I, which equals to 1 minus a. This is just a definition of a geometric series, and this a has to be strictly less than 1, between 0 and 1. And because our p is a probability, it is has to be existing in that interval. Okay, so then what we have here is p, and this expression now just becomes, so this a here is our a there. So what we get is the following. expression here. So that's the MGF of the geometric. Now, in the next step, we are going to calculate the first and the second moment. And the first moment equals to the derivative of the first derivative of the MGF, and the second moment as the second derivative. So e to the x equals to m of x prime t. So let's start calculating the first derivative with regards to t in this expression here, and that is of this MGF that we just calculated with respect to t. All right, and that is, I like to write it in the following terms. So we have p 1 minus e to the t, 1 minus p, like this, and we have a minus sign here. And that, before we take the derivative. So let's take the derivative and see what we get. So what we have here is a expression where, let's see here. I'm just thinking about the what is it that we have. So we have an expression inside here, and we have a minus here. So let's start taking the derivative of the outer function. So that's just 1 minus p minus 2, and then minus 1 jumps down, and then we take the derivative of the inner function here, which is just minus, it's minus 1 minus t, so that's gt, 1 minus p, like so, right? So just double check. So we're getting this down here, and then we're going to take this derivative of the inner function, that's minus t. Yep, that looks right. Now we just simplify this. We get p 1 minus e to the t minus p squared. And we have two minuses here, and they cancel each other out. And then we're left with e to the t 1 minus p. So there's one important thing that I forgot to mention, which is when we take the expectation over x, well, we'll use the MGF to calculate this expectation. We're doing it with respect to t equals 0. So technically we have to write t equals 0 here. And now I took the derivative without, setting t to 0 to begin with, because we're starting by taking the derivative and then we set t to 0 here and see what we get. So let's do it in this next step here. So I'm going to say t equals 0. Well, if t equals 0, you get e to the 0, which is 1. E to the 0 is also 1. So we're left with 1 minus, let's see, there's one thing I did wrong here, which is this p should be up here, right? It should be, it's this p here. It's obviously not squared to the minus 2. So it should be here. So what we're left with is P. We said that this E2 is 0. Sorry, yes, so 1, e to the t, e to the 0 is 1. Getting 1 minus p 2 squared 2. Okay, so some, almost there, just some more simplifications to get the expression, the most simplified expression. So what we have here is that this is obviously Q, and that is obviously Q here. So what we have is P Q 1 minus Q squared, and now this 1 minus Q is P. Just taking around the complement, we get P to the Q P squared, and that is QP, which is exactly what we wanted to show. So now we've done the expectation of over X using the MGF instead, which was slightly a little, extra work, but it's nice to see that it actually adds up in the way that we expect. So let's move on and take the figure out what the second moment is. So this derivative will be a little ugly, but bear with me. So expectation of x2 now, and that is, as we said by theorem 645, is the second derivative should be towards there, like that. And that is, so let's start by copying the first derivative. So where are we? We are here. Let's copy this, because that is before we set it to t equals 0. So this is what we want to calculate the second derivative. All right, so now we have all kinds of messiness going around here. We have to use the chain rule, we have to use the product rule, and all of those different rules here. So I should just add the following to make clear that we're taking the derivative of this with respect to t. All right, okay, so let's start by thinking about let's write it in the following form, just to make it absolutely clear what we are going to take first and second. And then we write this in the following form: to the t 1 minus p minus, like that. We're going to start by taking the derivative with respect to this, and then this just gets along, and then we take the derivative with respect to this, and that just goes along. Okay? So the derivative of this first one is fairly easy, it's just itself, and this 1 minus p is just a constant now, so it goes along, and this whole expression here stays as it is, and then we plus here. Now this goes along unchanged, and then we take the derivative with respect to this outer function and then the inner function. Okay, so the outer function becomes 1 minus 2. Minus 2, and the inner function stays the same, minus p, minus 3. Now we take the derivative of the inner function, which is, as we did earlier, let me just move this whole thing a little bit to the left to make some space. Like that. Now we take the derivative of the inner function, which is minus 1 e to the t 1 minus p. God, that's a ugly expression. So let's try to simplify that a bit and see what we get. I'm going to do the following to make it a little easier to read. I'm going to set all these guys. This is going to be q. This is going to be q. Could have done this earlier, obviously. Right like this. And we're going to also, for the sake of simplicity, we're going to now set, well, it's already there. So we can set t equals 0 in this next line here. So it means that all these exponentials become 1. So they will disappear, make things a little easier for us. So then we have a q multiplied by 1 minus q minus 2 plus, we have now, let's take the constants first, so the two negatives, so we get a 2 here, and there's a q, there's q here, and then we multiply by 1 minus, this is 1, that's a q, minus 3, and that's a 1, and that's another q here. Okay, it's getting simpler and simpler. And now I'm going to set all these 1 minus q's as p's. I'm getting q, p squared plus 2q squared, those two multiplied, p to the power of 3. So we're almost there now. I see this is getting simpler and simpler. Now we're going to, I missed a p here. So we're going to just remove 1 here. All right, 2. So we have p2q plus 2q2. Right? Wow, I see that I missed a p here as well. So this p did not move along. So this, it should be like that. Sorry about that confusion. Okay. And so what do we do here next? This looks still a little ugly, right? Now we're going to just basically simplify. Let's see, we're going to simplify by moving, going to move this, let's do the following, p to the, well, going to extract it, factorize out a q. This is just to make it a little simpler. I mean, we could already stop here because we are almost there. We would just need a little bit more simplification to make it easier to read. So we have a q, we're taking out a q. So we're left here with is a p plus 2q, right? And that's all divided by p to the t. Okay. And 2q, I'm going to unpack this a little bit. So it's 1 minus p here. So what we get is, let's do the following, that we take this whole inner expression here. We're going to do this separately, so we do it to p plus 2 1 minus p, and just factor out this whole thing and see what we get. So we get here p plus 2 minus p, which is obviously, well, I think there's something, let me just double check this guy here. 2q pq. Does this looks right from the following here? qp plus 2 minus, yeah, this looks right as well. P to the plus 2 minus p minus, all right, so I see what I get wrong here. This should be a 2 minus here, 2 minus 2p, like that. Okay, my bad. And what we are left with here is a 2 minus p, correct? 2 minus p here, and that is the same thing as 1 plus 1 minus p, which is a q here. Now we're left with 1 plus q. Oh my god. So this is a little extra complication of kicking around things, but everything to get it a little neater. So this is then q 1 minus q p2. All right, I think this is as simple as we can get it. And now we are just going to calculate the variance. So the variance of x is exponential, the expected value, sorry, of x to the 2 minus e to the x, like that. And we have already all those pieces, so we can just put everything together. So we have this minus here times, well, let's duplicate this guy here, and then we go up and find our first, like that, and we copy, move it down like that. Let's clean it up like so. Okay, and now we just simplify this whole thing by taking, let's see, did I do this right? So it should be in the other direction. So let's move this guy here, and this one here, this expression, yeah, 2. Okay, so now we're ready to go. So we have q plus q2 minus q2, and that is simply qp2, which is the variance of the geometric, which was what we wanted to prove here. And that's the following.